Again, a full summary of everything that we've seen so far. Those are Maxwell's. These are the Biot-Savart law and the Gauss law, the Gold law. And here are some equivalent mathematical forms that in some cases might be easier. Right? We've seen both of these now, and you can apply these as well, and sometimes you get it easier your answer than if you would have gone through this full calculation. And once you have your electric field, your magnetic field, there you go. You can get your forcers, and that's all there is to it. Now, up to this point, we haven't really talked about the dynamics part yet. Because, of course, if you have a particle floating around and there is a magnetic field or electric field, then once you get your electric field in your magnetic field, you can calculate where these particles will fly to. But as a result, the whole setup of the electric field and magnetic field will change, right? Because all of a sudden charges and currents are somewhere else than they were a second ago, so that means things have to be updated. And we haven't really looked at that part yet. And we're not going to today. This is something for next week. My promise for today is, let's see if we can rewrite all of this into a new mathematical form that encapsulates the exact same information, but in a way that, first of all, that's much easier. It's more abstract in the sense that it's harder to envision what these things mean. But it's more easy in the sense that mathematically it's much more economical. And here's a real cool thing. I will give you the general solution. So you will have by the end of today a full solution for any situation, in any circumstance, in all of electrodynamics. So this is why I'm saying today might be a lecture that, you know, everything will come together, and really you can just, you know, quit this course at the end of today because I'm going to give you the full solution, and that all done is just application. Of course, life is a little bit more technical than that, but I am not lying. I will give you the actual solution for all electrodynamical situations, and I hope you will see the beauty of this, how ridiculously beautiful this is going to be. Now, before we go into those details, one more time, how many equations are there in the Maxwell's at this point? If you take into account their full vectorness. These were 8, right? This is 1, it's a scalar equation. This is 1 scalar equation, these are vector equations, each are like 3, so in total you have 8. But then again, we're looking for only 6 thingies, right? 3 components of the electric field and 3 components of the magnetic field, so we have more equations than we have things that we're looking for. So that means that there is a certain amount of redundancy here. So at the very least, we should be able to remove the redundancy and rewrite this into some formulation that has less than 8 equations, because we don't need 8 equations in order to solve 6 things. So how many do you think we're going to end up with instead of 8 equations?
If we have to solve 6 things,
yes.
I guess it would be 6.
Yes, but the answer is 4. We're going to get 4 equations that's going to solve everything. So even if we have removed the redundancy in the sense that you need 3 components for electric field and 3 components for the magnetic field, then still you would have a redundancy. Apparently you only need 4 equations to solve all of electromagnetism.
So one is a repetition or a combination of 2
yes,
others.
There is some, I wouldn't say linear combination, because it's certainly not linear per se, or I don't think it is. But you're right, I mean, some of these equations carry too much information, or carry something that one of the other equations already said. And the idea is to get that out. Now, just as a sort of flow chart, I'll already tell you what we're going to end up with before going to other mathematics, because mathematics might be, it's going to be technical, but you know, what can we do? So, it's going to take us a while, but once we get there, again, we're going to have less equations, and they're going to give you the general solution for all 4 of them. So you're done for all entirety for the whole of the course in principle. Now, before we go to the calculation, let me tell you what we're going to end up with. All of this is the hard part, so you got it. We're going to end up with an equation for this thing. It's called phi, it's called the scalar potential. People do electromagnetism with Benedict, I think. I walked by this morning when he gave the lecture. I think I actually saw the thing on the board. Rodrigo, there's another person who's following the course.
Ahmad.
Yeah, exactly. So, okay, just from context alone, this is how Benedict pronounces your name, right?
What?
You very gutturally pronounce his name.
Okay.
And it sounded, there's a story involved there. And I'm guessing what the story is.
What story is there?
No,
Is there a story?
No, has Benedict talked about this morning? Has he talked about the scalar potential?
Yeah.
Yes. Okay. Good. So we're going to look for this particular thing, and we're going to also look for another thing, a new vector field, and it's called the vector potential. So if you have the scalar potential, which is only one function, and you have the vector potential, which comes with 3 components, so you have in totality 4 functions. Knowing these two is completely equivalent to knowing all of this. So that's what we're going to look for. Again, we will remove the redundancy, and I will also tell you the general expressions for both of these for all situations. That's the plan. Now for this part. Now, you know what, maybe for overview's sake, let me say one more thing. And if you're not catching this part, don't worry about it. We will get to it in a few lectures from now, but for the people who have done relativity in one form or another, you know that in relativity, you have particular observables that go together into one vector. Now, of course, x, y, and z go together in one vector, right? It's called a 3 vector. It's just literally position in space. Or momenta. There's a certain amount of momentum in this direction, that direction, that direction. Velocity, acceleration, these sorts of things. But in special relativity, you have seen probably that whatever happens in space also has a temporal component. There's a time component to the thing. And those things can be grouped together into this bigger thing that's called a 4 vector. Now, a very famous example of a 4 vector, here's a 3 vector for position. But if you add time to the mix, you get something that's called a 4 vector. Now, to be clear, it's not called a 4 vector just because it happens to be 4 numbers grouped together into one vector. Yes, it is a vector of 4 thingies. That, by definition, does not make it a 4 vector. It's a 4 vector because this particular grouping of observables together obeys certain rules. And just out of curiosity, does anyone know what the rules are that this particular combination of 4 observables obey? Line element is not a rule. Okay. Gaussian? There. Oh.
Lorentz invariant.
The magnitudes invariant.
Lorentz transformations. If you do a Lorentz transformation, you can turn a little bit of x into a little bit of t. Or if you do it in another direction, Lorentz transformation, you can turn a little bit of y into a little bit of t. But you can mix these things together by Lorentz transforms. Yes, this is why they are grouped together into one thing. If I would replace this by, I don't know, temperature or something like that, yes, I would have a vector of 4 thingies in it, but they have nothing to do with each other. You can Lorentz transform all the way that you want, your x will not become a temperature. Now, another famous example of a 4 vector is if you have momenta in 3 directions. And again, there's another component that you could add to the mix that go into each other once you do Lorentz transforms.
Energy?
Yes, the energy. Yeah, but yeah, sure. Divided by the speed of light. So this also is a 4 vector. Moment, if you do a boost, which is a technical term for doing a Lorentz transform, you can change a certain amount of momentum into an extra amount of energy. Now, of course, you notice this in a certain way is already true in Newtonian mechanics, that if you have a particle flying in that direction and you decide to travel along with the thing, then that thing will have less momentum in that direction for you, right? But it will also have less kinetic energy because you're traveling along with the thing. So apparently, changing coordinate frame and starting to move along, doing a Lorentz transform, will not just change one of these numbers, your energy will change accordingly as well. Now, the exact rules are, again, the Lorentz transforms. And all vectors that go together where the 4 components are connected to each other by Lorentz transforms, or more technically spoken, by the Minkowski line element called 4 vectors. Of course, we will do this in in week 4 of this series. We'll go into full detail about these things. But here's a thing, and here's 3 other things. These together again form a 4 vector. This is not trivial, right? Just as that I cannot just simply put 4 numbers together into one thing and then all of a sudden it becomes a 4 vector, as in that they obey Lorentz transforms. That's certainly not true for all variables that I put together into one vector. The same thing should not necessarily be true for these 2. 3 of these, with this added to it, there's no prior reason why you would think that is a 4 vector, but it is. Nature has decided that this is a 4 vector. And that means that automatically, at the moment that you've rewritten all this messy stuff into this, you can immediately write it as a 4 vector, you can immediately do special relativity with it. So this is another reason why going through this pain is going to serve us well. So again, we're going to remove redundancy, that's advantage 1. Advantage number 2 is I'm going to give the general solution for all cases. And advantage number 3 is it's very easy to turn this into special relativity because these things already form a 4 vector by themselves. Okay, so this is why we're doing it. Now we're going to do it. All right. Now, for didactical reasons, I decide to start with the static case. Now, the static case just means all time derivatives are going to be 0. I can also immediately go to the full case, but I think it's a nice warm-up exercise to first do it in the static case. So, let me just write down what the Maxwell equations are in the static case. Well, you know what they are. It's just literally what it says over there, except all the time derivatives are going to be 0. So, just in case things do not move about. Do you see that there's a nice piece of symmetry going on there? I mean, if I would take these 2 and I would replace the inner product with a curl, then I sort of get these back. Oh, you know, I replace the inner products by cross products and I replace E by B, then I sort of get the other side back, right? So, I mean, there is a certain amount of symmetry there. The divergence of the magnetic field is 0, whereas the curl of the electric field is 0. And the curl of the magnetic field is non-zero, just like the divergence of the electric field is non-zero. I mean, there is a certain amount of symmetry there. Now, let's do the following. There's a certain law in just vector calculus. I'm collecting my thoughts here for a moment. Oh, there you go. There's a certain law. This is not physics, this is mathematics. If you take the, if you take the gradient of any random function, f, it's a scalar, it could be a constant, could be a function, could depend on time, space, temperature, whatever. But if you take this thing, you take this gradient, and what you end up with, this thing by itself is a vector, and of that vector, you take the curl, it will always be 0. This is a mathematical statement. In fact, this is going to be one of the exercises. You can easily prove this for yourself. It's not that hard. Okay? So, this is just a mathematical fact. Now, let's exploit this mathematical fact by looking at this equation here. Because we know that we have the curl of something here, namely the electric field. And apparently in statics this should be 0. So you might as well say, oh, you know what? If that's the case,
can we write it?
Then we can just say, well, the electric field then apparently is a gradient of some function. Right? This is true because of mathematics. Excuse me, this is true because of mathematics. This is true because of physics. Well, might as well just connect these things together and just say, you know what? If this is the case, let's just plain define the electric field as the gradient of some function. Now that function, I call it f here, but in this context we call this phi. This is what we call the scalar potential. Now for reasons I will get to into a moment, it's defined with a minus sign. Now you see that you can put the minus sign there without any loss of generality, right? I mean, this is true for any function, scalar function, might as well put an additional minus there. Why? Because of a reason I will go into in a moment. It's advantageous for multiple reasons. So, what do we have as a conclusion here now? Just from mathematics alone, apparently, I can make sure that the third Maxwell equation is perfectly obeyed if I write my electric field as the gradient of some scalar function. But I've only taken care of this one though. I mean, I haven't looked at what this other condition that the electric field must obey, but this one is perfectly solved if I define my electric field as the gradient of another function. Okay, this takes care of Maxwell number 3. Okay, fine. Now, before we continue, why do we call this a scalar potential? Why do we call this a potential? That's a scalar is obvious, yes, that follows directly from this mathematical fact. But why do we call this, yes?
I'm not sure if this is related, but
Okay.
in classical mechanics, you can look
The
at
answer
the
is yes,
force.
but please continue. I know where this is going. Yes, go ahead, yes.
Okay, well, the force can be seen as the gradient of the potential, and because the force here is just a scalar multiple, well, the electric field is a scalar multiple of the force, then it's
Yes,
similar,
that is
I guess.
exactly true.
Okay.
And I'm going a little bit off of a tangent here, but it is important. So let's connect it to classical mechanics, which is another theory that I am really fond of. There are theories that I'm not fond of, but most of them I like. This is one of them.
Do tell.
The statement that you're making is that, well, you can write a force, classical mechanics, again as minus,
Yeah.
right? This is how it's defined, the potential energy.
Yeah.
Yes. Okay. But you can only do this under one condition, and it's not always emphasized in course in classical
Conservative
mechanics.
force.
Yes, but what does that mean, conservative force?
Path independent.
Yeah.
That the curl is 0?
Yes. Yes. In different statements, and they are mathematically equivalent. You can only do this under the condition that the curl of this particular force is 0.
Yeah.
Only then is this possible, and that is, by the way, the exact same reason that I'm applying here. The fact that I know that the curl of the thingy is 0, that allows me to write it as the gradient of a potential. So this was your question, right? Whether this corresponds is, whether it's the same thing. It's the exact same argument. But in classical mechanics, let's connect everything together now. Yeah, let's do that for a second. It's a tangent, but it's a fun tangent. Suppose, okay, so this is true. That this is true is due to this fact. So this is equivalent, yes. Now let's suppose that, you know what, I'm going to integrate this over a surface. I mean, if this is true, then the integration on both sides is also true, yes? Okay. Now, does this look familiar? See earlier today? This is Stokes' theorem. So that's the same thing as saying, oh, in that case. And this must be true, right? This is Stokes' theorem.
Yeah.
In fact, this is how we got Ampere's law that we have here. Now, physically, what does that mean? This thing here. It means that if you start here in a three-dimensional space, and there's a certain amount of force that the particle feels here, and you will move it all the way to some other point in space. But look, it's a closed loop, so this only holds if you also go back. Then apparently it's the same as if you have not done anything at all. Right? And notice that this condition doesn't specify in any way how you must have walked back and forth. You're allowed to walk towards this point in this way, but if you want to walk back in some somersaulty fashion, you're perfectly allowed. This thing does not tell you how you have to walk back and forth, but the fact that this will give you 0 regardless how you walked to and back is what we call path independence. That apparently it doesn't matter how you move through space, a conservative force is by definition a force where it does not matter how you've moved back and forth, you will always end up with the exact same thing. Let's make one more special thing. What do you call a force times a distance? Work. So apparently, the fact that you walk back from here to here, that costs you a certain amount of work. But once you walk back, apparently you get back the exact amount of energy that you put in, you get back, yes? Because otherwise it could not have given you 0. This is just really the sum of the energy that you put in and the energy that you got back. The fact that it gives you 0 is the same thing as saying that this force was such that the energy is a conserved quantity. This is why it's called a conserved force. So we have 3 equivalent statements here. If your force obeys this, it can be written as the gradient of a scalar function. If your force can be written as this, it also means that it doesn't matter how you walk back to and back, you will get 0. It's path independent. Third statement, the amount of energy that it costs to walk there and the amount of energy that you get back is the exact same number, conserved energy. This is why it's called a conserved force. One final statement, tangent. One final statement. That also means, maybe I shouldn't go here, but I'm going to try anyway. That also means that you can define an energy to begin with.
Yeah.
Right?
What we did with the gradient thing?
Potential.
Potential energy, yes. Because listen, if it would have mattered how you walked here, what we now see, it doesn't matter if you walked from here to here in this way or in this way, it will cost you the same amount of energy, right?
Mm-hmm.
That's what this thing tells you. Now suppose that it did matter how you walked from there to there. Is the amount of energy that it cost you, would that number would have meant something to you? This is why I was doubting whether I should go into this, because to do this real justice, takes 20 minutes or so.
Direction or something?
Yeah, well, let me try just for a second, and if this is not connecting, don't worry too much about it. But suppose that I have this book here, yes? And it feels a force now, namely gravitational force. And I decide to lift it from here to there.
Mm-hmm.
And I can do it in 2 ways. I do it either this way, or I do it in this way.
Mm-hmm.
Now suppose that it would have cost me a different amount of energy to make it go from here to here in this way than it would have in this way.
Yes.
Then the potential energy or the gravitational energy of this thing would have been a different number, yes?
Mm-hmm.
So suppose that you weren't around when I lifted the book from here to here. You don't know whether I did it this way or that way. And I've told you what cost me 5 joules.
You have 2 different answers for the same
Yes.
position.
So that exactly. If I tell you it cost me 5 joules, you have no idea how I did it, right? So that means that the energy all of a sudden has lost its significance as a physical parameter. So here's a 4th equivalent statement to conservative forces. You can only unambiguously define what is meant by a potential energy because of its path independence. If it has path dependence, then the amount of energy that it costs you to bring from here to here has no meaning whatsoever. It doesn't give you any information on how you did your process. So this is why potential conservative forces are extremely important in mechanics. Without it, you cannot define energies. Well, you can define a number, but the number doesn't tell you anything. The number 5, potential energy, tells you nothing about how you did your process. So you can extract no physics from it. So if any force in physics does not obey this particular rule, that its cross product or its curl is 0, that's another way of saying that there's no point in defining an energy for that thing. It has no meaning. Now, then the question is, okay, are all forces, was nature so kind to us to make sure that all forces are conservative?
There is one right there.
Which one is that?
Magnetic force.
The magnetic force is it or is it not?
Well, the curl is not 0.
That is true. In fact, when I used to teach a course on the physics of energy, and this was part of that course, explaining these sorts of things. And I let them calculate through all the fundamental forces in nature. So I had them do this for the gravitational force, Newton. I had them do this for the electrical force. And then you find that all of them are indeed conservative. In fact, you can prove that if a force only depends on distance and not on angle, it automatically is conservative. That's an exercise you can do. But fortunately, gravitational force, Newtonian, and the electrical force only depend on distance. So therefore, these are conservative, and so therefore, there's a point in defining energies for these things. But yes, then the big question always was, how about the Lorentz force, the magnetic force? Because its curl is not zero. That's not zero. Even in the static case, it's not zero. So does it mean there's no point in defining magnetic energy? Does it mean that that number doesn't matter? I have to stop somewhere, but there is a subtlety there. Okay. But I cannot help myself. If you bring it from here to here, the way that you bring it there, in this case, also not just depends on how you got it there, it also depends with what velocity you did it. But that means along the way you encounter different electric fields.
But don't we have the same problem in special relativity? Because we can go to one point to another, but depending on the referential, the distance that we have is different. So the path and the way we travel.
Yes, but now you're mixing up a couple of things. As long as you stay in one reference frame, the energy is going to be well defined if your forces are conservative. Yes, you're right. If you midway change also your reference frame, now all of a sudden your energy becomes a different number. That's true, but that's cheating because you're now just changing the setup to begin with. Mm-hmm. As long as you stick to one reference frame, the same holds. Anyway, the magnetic force, if you properly include the fact that this velocity will also introduce extra electric fields, then the combined thing still makes it conservative. And that's good news for us because that means that all fundamental forces are automatically conservative and therefore energy can be defined to begin with, let alone that it is constant and Noether's theorem and these sorts of things. Anyway, so yes, Alec, this is this is a brief version of this longer story. Okay. So going back to this longer story here. Where were we? Oh yeah. So the fact that its curl is zero means that you can write the electric field as minus the gradient of a scalar function, and that takes care of the third Maxwell equation. So we've already sort of removed one redundancy, right? We don't need the third Maxwell equation anymore at the moment that you write your electric field as minus the gradient of a scalar function. So one equation is now out of the system. As long as you say, well, you know what, the electric field is minus the gradient of a scalar function, you're never going to need the third Maxwell equation anymore.
But it's
So-
not just introducing another equation.
No, this is definition. What if I were able to write all Maxwell's equations and there's no electric field at all anymore? Everything is just written in terms of scalar potentials and vector potentials. And then I have no extra, then I just have 4 equations ultimately. So, now, how about, there's another rule that the thing must obey.
But then shouldn't we have a problem for this one, the
when it's not
cross
static.
product with E? If we can write it as a scalar of a cross product, will it be equal to 0?
Where?
The 1, 2, 3, the third one. This one. If I plug in E and write it as a gradient, shouldn't it be equal to 0 with the same law that we have already here?
Yeah, but remember that I'm now deliberately only looking at statics, yes? So in a moment I will do the same exercise, but now including this part. But for didactical reasons, I first do it for the statics, and you're completely right. But I first want to show you what happens, and then I'm going to add the fact that it's not really 0 to the same thing here. So just bear with me for a moment, sticking to statics for now.
So it's not conservative if it's not static. It's not a conservative force.
The electric field by itself is not, but again, your force then automatically also include the magnetic field, and the combined effect is again conservative. But again, sticking to statics for the moment. Now let's see what then this thing should obey. And just to be sure, I mean, your question now was a second ago, we have introduced another equation, right? No, we haven't. We just written down a definition. And the definition is, yes, it's an equation in the sense that it says something equals something else. But it doesn't tell what the thing should do. It just tells you what it is. Do you see the difference between the two statements? Here's an equation. F equals m times a, or dp dt. Yes. Here's another equation. 2 times f is the same as s plus s, is the same as s plus s. Agreed? Have I added extra information to the system?
What was the second one?
2f equals f plus f.
Okay.
No.
No.
No. So just the fact that I have another thing with an equality sign in between doesn't mean that I have extra information. That's very much the same thing here. I've just defined the thing in terms of something else. Or here's yet another equation. Okay, suppose that 2x equals 15. Okay? Of course, everybody knows what x is, but that's not the question here. 2x equals 15. I have one equation that specifies x. But here's another equation. Y, new variable, equals 5 times x. Have I added information to the system? Have I? I mean,
You wouldn't know how
Because
y
x is still
Well, you wouldn't have known what y.
No. What I do is I define what y is. I say it's, well, whatever x is, 5 times that is y.
Mhm.
I have not added anything else. I've just said, well, I introduce this new thing. I call it 5 times the thing that I already had.
But all of Maxwell's equations are defining properties in terms of other properties, right? Because you start with the Coulomb's law and then Biot-Savart law.
Yes, I agree in a certain sense. Some of this is also just definition, right? Because they come from Coulomb's law and from Biot-Savart, which are definitions of the electric field and magnetic field. That is very true, but how they are connected to each other is certainly not trivial. That doesn't follow from the definitions alone, right? So this one, for instance, is not a definition. That's really what nature does. Now, the only thing that I'm saying here is I have an equation for my electric field. And just saying, well, the electric field is 2 times the Sidley field. They say, but now you have 2 equations. No, I don't.
Yeah.
I have only one piece of information spread out over 2 equations. And that's very much the same thing here. I have my electric field, and it's the gradient of the Sidley field. It's the definition of the Sidley field, if you want. That's all that it does. So it's not new information. So I really, by writing this, I really removed one actual equation for my system. But again, I haven't specified yet what this new thing does. I'm going to call it the scalar potential now, so I'm going to leave you out of it for now, but this is the scalar potential, okay? I don't know what it does. Well, fortunately, I do know what E does. E does this. So, well, if I know what my E does, how my E is defined in my scalar potential, I can also find out what my scalar potential should do. So, I'm going to take this thing, I'm going to substitute it in my first Maxwell equation. So I get this thing, the divergence of this thing with the electric field, but the electric field I just defined in terms of this, and then according to Maxwell's first equation it should equal this. Now this, and last week we started the main lecture by listing all the symbols. This is what, do you remember what this was called? Just to Laplacian. So what we now have is, let's get to the other side. So what we now have is that the Laplacian of this new thing should equal minus the charge density. How many equations are this? 2?
No, 3.
The red one.
Oh. No.
That's just rewriting the first.
Only one.
It actually is one.
Well, that is the question, right? Well, is the Laplacian of a scalar, is that itself a scalar or is it a vector?
It's a scalar.
It's a scalar.
But if we just look at the definition, like it's equal to a scalar. So.
No,
Yeah, I
that is
think
right. If this is not a scalar, you would run into trouble because it apparently is set equal to a scalar.
Yeah.
It better be a scalar.
I mean,
It is though. And this is why I wrote down last week a definition of what Laplacian means for a scalar field. This thing, let me write it out for a moment. This means this. Whatever the scalar potential is, take its derivative with respect to the 3 coordinates, do it twice, add the results together, you will get a scalar. So look what we have here. Again, how many equations were this? The third Maxwell equation? 3. We've reduced it here to, by this definition, to 1.
mm-hmm.
How many was this?
1 plus 1.
Also reduced to 1. So these two, both of them, are completely encapsulated into this equation. We've reduced 4 equations into 1 now. All the information that was here in both of them is all into this one now. So there you go. We lost 3 equations out of the 8 that we had. Now that is process, yes? Making progress here. We've removed redundancy. So one more time, just for completeness. This equation tells you that your scalar field, scalar potential, exists. The fact that this is true allows you to write it as a scalar potential, so it just tells you the thing exists. And then this one tells you how the thing behaves. And all is together grouped in this to this one equation. So there's that. So we've cleaned up a lot. Now we call this a potential because of, well, this is what we do in physics. Every time that you have something of which the derivative gives you a force, that's just the definition of things. If you have an object and you take its derivative and it gives you a force, then the thing you call a potential. That's just nomenclature. Just like we call this potential energy. Why? Because if you take its derivative, it gives you a force. Very much the same way. We have a thing here, its derivative gives you, well, up to a charge, gives you the force, so therefore this is a potential. That's just how we call these things. Things of which the derivative is a force, you call potentials, so therefore this is a potential. It's a scalar, so it's a scalar potential.
And for B, we can do the same and say that set B as a cross product of something, right? And that's how we...
Yes, actually.
And we do exactly the same thing on the other side, and then we have the...
Oh, perfect, let's do it right now. Because we've taken care now of this one, and that one, all into here. Let's do the same for the magnetics now. And Claudia, you were saying?
So instead of writing B, I can write B as a cross product of something.
Why?
A, I guess. Oh.
No, but why?
Because of the same rule before, like using math.
Yeah, oh, sure, but I cannot use this particular fact. I need a different rule.
Like the divergence of the curl is 0.
Yes. One of the exercises of last week was that if you take the divergence of a curl, it is always 0, regardless of what f is. Regardless how it depends on x, y, z, temperature, and all these other things, the divergence of a curl is always 0. Okay, now we have a divergence of a thing that is always 0, namely the magnetic field. So by this mathematical fact, this is what you get with tangents. It gets in the way of what we were actually trying to tell. I don't know what workspace anymore. So by the mathematical fact that this is true, we don't have to prove this. We did this last week. This one is an exercise to prove this. But by this one, you can say, well, I have something of which the divergence is 0. That's Maxwell's second equation. So you very much just say, well, you can say, well, in that case, might as well call B the curl of a thingy. But the thingy has to be a vector. Now, you will not be surprised that that's what we're going to go to the vector potential. So, there you go. Again, I'm not putting new information in. I'm just saying that the thing exists. There is a function A, vector function such, if you take its curl, you will get the magnetic field. Question. We've taken care of this equation. At the moment that I write my B as the curl of a new function A, I automatically obey Maxwell's second equation, but it just tells you that this vector potential exists. It doesn't tell you what it does. So how can we find out what the vector potential does?
Same way, we replace B by the in the fourth equation, like what we found.
Exactly. So the second equation tells you that the thing exists. If you want to know what it does, well, here's something that the magnetic field does. You know how to write the magnetic field in terms of your vector potential. Just plug it in and see what happens. So you get B, but B we saw you can write as itself a cross product. So you have the curl of a curl, and that by itself, in the case of electrostatics, should give you this. So, look at it. There you go. And now we've taken care of this equation, and we've taken care of this equation. We never have to look at Maxwell's equations anymore. In the statics, still only looking at statics right now. If somebody gives you a charge density rho and a current J, feel free to go through these exercises. We've seen during tutorials that that typically takes you a while to get to the answer. You know what? Might as well do it like this. Somebody gives you a charge density, solve this equation instead of the Maxwell's, and you get your electric field. Well, you will get your scalar potential, but then you plug it back into here, you get your electric field. And if somebody gives you a current, well, instead of going through the whole Maxwell's equations, feel free to, it takes a while, see the exercise of the tutorial last week. Instead of solving the Maxwell's, just put it in here. Solve this one, find the vector potential, put it back into here, you get your magnetic field. All solved, no Maxwell's equations necessary. How many equations are this, the second one?
Three.
Three. So how many equations do we end up with in total? That's the 4 that I promised. We went from 8 to 4. And we've retained all the information. So there was a huge amount of redundancy in the original Maxwell's.
Don't we have a time factor in the G thing?
The J.
The J, do we have a time factor? Since it's like the number of charge per volume per second or something like that? So
Yes, but we're assuming steady currents here.
oh yeah, okay.
Yes. Again, we're still in the situation of statics. If you don't have a steady current, you have a pileup of charges, you end up with an electric field, and your electric field will change in time. Now, we can do a little better than this.
Gideon, sorry, could
Yes.
you just point out again, what are the 4?
This is a vector equation, so that's 3 components, that's 3 equations.
Okay.
This is fully scalar, that's 1 equation. In total, 4 equations, whereas you started with 8. But we have retained the same information. Man, I love this theory. Oh, look how beautiful it is. And it gets better. Because let's do a little bit of rewriting. I mean, this is ugly. If somebody gives you a charge, a current, a J, and then you have to solve this, well, you're probably, still in the mathematical woods. How do you solve that? Let's make life easy. Here's a promise. We're going to take this thing. No. Again, here's the hard part. We will end up with this equation. Well, I will show you how this works. But just to show you where we're going, this you itself can write as such. Now suppose that we succeed in doing so. Yes? Do you see that this equation and this equation are really just the same equation, the same mathematics? I mean, sure, there's 3 of these, but all 3 here and the 1 here are all the same thing. Take 2 derivatives of each spatial component, add it together, set equal to such and such.
But sorry, if oh yeah, it's a okay.
Yeah,
It's
yeah.
a
So
vector, yeah.
this is this again. If you go back to last week when we introduced notation, this thing, the Laplacian of a vector function, is the same as the Laplacian of its x value. But then you also have to take the x value of the current. Okay, so this is just shorthand for 3 of these equations. Right, these are the 3 that I was talking about. This 3 plus that one gives you the 4. But this one, this one, this one, these are not minus signs, this is numerating. These 3, these 3 are the exact same thing as this one. It's the exact same, in all cases it's just a scalar Laplacian equals something.
So when we add up every terms, we should find the not exactly, I guess.
No. This is equation completely separate from this one. This is completely separate from this one. 4 equations, 3 equations. Now, what is my big point here? My big point here is that I have 3 equations here that are the exact same mathematical structure. Laplacian of a scalar function be it ax, ay, az, or phi, Laplacian of a scalar function equals something. But that really means, from a mathematical point of view, that I only have one type of equation to solve. If I know the general solution to such a type of equation, I've solved all 4 of them in one go. I will give you the solution, and it's up to you to show in the tutorial exercises that it is indeed a solution. So by the end, once we've gone through these dots, you will have the full solution to all situations. So, some good news there. Now let's look at the dot here. Okay? It starts with this thing. The curl of a curl. Now, you can prove that that is equal to this is equal to this. It's just a statement of mathematics. You can prove this for yourself, not too hard. You know how curls work, you know how Laplacians work. Just write out left side and left-hand side. So write out this one and write out this one, you see it's the same thing. So this is just still the same statement. Now my claim was, oh excuse me, minus sign. Yeah, it's automatic because I'm so used to having this minus sign. Here's still a plus sign. But suppose that it's in some way we can show that this part is 0, the first part. Suppose that we can. Then we're exactly where I promised we would end up, yes? We would get this one here. So the question is the divergence of the vector potential itself 0? If so, then we can get rid of this one and go to this one instead. And then we have the beautiful situation where 4 times the same equation. But we have to prove whether that is the case.
Maybe.
Yes?
If it's supposed to give a scalar thing, oh no, there can still be variation of it. But
Well, it's good to spend a little bit of time on there. I mean, this thing will give you a scalar, yes?
yeah, but I was thinking if we can prove that this scalar is constant or something like that, then we know that its
sure.
gradient will be like equal to 0.
Yes. That is a good point. If we can find that this is the divergence of A is 0, or is constant, yes, then its gradient must be 0. I agree.
And maybe we can use B or something because we have a.
Now, the bad news is there is no a priori reason that the divergence of this vector potential is going to be 0 in all cases. That's the bad news. Yes?
Sorry, we were just wondering, we don't see the difference between the divergent, or like nabla times nabla in parentheses A and the Laplacian times A. So because you have the nabla twice, but what's the divergence?
This looks 0-ish, yes? Because you have a divergence, and on it you do this thing, so you have sort of twice the nabla operator. So isn't it exactly this?
The brackets are placed differently, right, in the case of the Laplacian, right?
Yes. Let's write them out. Let's write out this one and that one,
Yeah.
just to see that they're not the same. Because if they are, you're right, then it would say 0, and then it would make sense. So, it's a good point. Maybe after that, it's a good moment for a break. But yeah, let's do this. No, it's a good point. In fact, I remember when I taught the course last year, we ran into the same question, and I sort of forgot about mentioning this, and then people got confused, and I only found out later on. So it's good that you asked now, and I should have picked it up myself. Yes. So the question is, why is this not 0, the whole left-hand side, just on its own, regardless of what A is? Because, listen, you have 2 nablas here, so it gives you the, excuse me, it gives you the impression of a nabla square. So you have nabla square minus nabla square, isn't that just 0? No. Let's write it out. We have So let's start with the first one. So this term. Now, I'm not going to specify anything about what this A is. I'm not going to say it's this function or that function. I'm just going to say it's a vector, AX, AY, AZ. Then its divergence is going to be dxAx plus dyAy plus dzAz. That's the definition of this thing in the middle. And then of this thing, you're going to take the gradient. What is the gradient? It means the dx, dy, and dz of the whole thing.
Yeah.
This is the outcome. Okay, I'm too lazy to write out this whole thing another 2 times, but that's what it says. So this first term, this one here, looks like this. And it contains some secondary with respect to x, and there's a dx dy, there's a dx dz, etc. Now, how about Laplacian of vector A? That's this term. Just to check whether that happens to be the same thing.
Oh.
Remember the Laplacian of a vector meant take the Laplacian, the scalar Laplacian of each.
2 times.
So
So
Just take the second
delta
word.
x squared a plus and so on. B squared.
this is, yes.
Each component 2 times.
Oh, x squared. Right, that's just the definition of the thing. This thing is not that thing. So this thing is not that thing, therefore they do not cancel each other out, despite the notation giving you that suggestion. So that's a real good question that we went through this for a moment. All right. So all clear on this? This is not zero? Now the question still stands, and let's continue with this after the break, but the question still stands is, can we make sure that this maybe possibly is zero? The divergence of A is zero, or maybe this, or is constant, yes, so its gradient is zero. If so, this equation reduces to this much more easy form, that one. If not, then we're just in bad luck, but it will. But this is something for after the break. All clear so far?
Yep.
Good. All right, let's have a break. Let's continue 15 over here.
I mean, the bottom one.
I wrote the summary. Yet one more. Look. Maxification, blah, 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 blah. Last week, this week. As long as you stick to statics, you don't have to solve the Maxwell's equations. Solve this one and that one instead. Once you have those solved, I will fill in the blank in a moment for you, but once you have solved this, and you have your scalar potential and your vector potential, put them in these 2 things, and you get your electromagnetic fluids, and all is solved.
Okay.
Right. Now, what we were worrying about was whether maybe we could, fudge this away, make sure that this part is not there. We don't have to, though. I mean, in principle, this is a perfectly mathematically fine solution, but maybe we can make our lives easier, making sure that this thing is not there. Again, why? That's because if this is not there, then these equations are very much the same. There should be a minus sign here. There you go. Then, if we can make this zero, then you have 4 times the same equation, and you can use that one solution, and you're done for all time. If only we can make this zero. So this is something we're going to work on now, and it's going to bring us close to a particular instance of something in physics that happens very frequently, namely gauge freedom. If you have no idea what gauge freedom is, do pay attention, because it's not a feature of electrodynamics per se, it's a feature of many fields of physics.
Just like the degree of freedom of things like that.
You'll see. All right, so let me start with an observation. Here's a claim that I make. If I have a particular scalar potential, yes, some A. And suppose that I really want the thing to have divergence that is 0. So I really want this to be 0. So this one vanishes, right? And just make sure that this is 0. Suppose that I want to do that. Here's a claim that I'm making. Now let me build it up in a somewhat different way. One step back. Suppose that I have my scalar potential and I want a magnetic field to come out. I want to do it the easier way, but I think we can handle it a little bit more. Instead of just giving you a solution, let's check how we get there. Okay? I'm going to postulate the solution. Now let's build it up. We have seen that a magnetic field follows from your scalar potential in this particular way. Right? That's what we saw. This followed directly from Maxwell's second law. Second equation.
Isn't it 2 times the scalar?
No.
Okay, that's
2.
okay. I don't know. I thought it was 2 times the curve.
No.
Oh, it's because it was okay. We implemented it in the other part of the B, in the 4th part of the thing. Never mind. It's because in the 4th equation we implemented B and write it as the cross product of the curl of A, and then we have already a curl. It's just like that.
Oh, 2 times. You mean
Yeah.
nabla squared?
Yeah.
I thought you were missing a factor 2. And I was
No,
really
no.
confused there for a moment.
No.
You can though. I mean, if you want to put a factor 2 there, just redefine your A with 2 times smaller. Now we saw that this is allowed because the divergence of the magnetic field must be 0. Okay. Suppose that I say, you know what? Is this the only vector potential that will give me this particular magnetic field? Is there only one particular choice of my vector potential A such that this magnetic field comes out? You could tell by the sound of my voice maybe the answer is going to be no. There's more than one way to choose your vector potential such that this magnetic field is the same. That you can do something to the vector potential such that your B field will still be that same magnetic field. In fact, you can already sort of tell, but let's do it like this. Suppose that we replace this vector potential by maybe a new vector potential. Let's call it new vector potential with a prime. And we're going to define this new vector potential as the old vector potential plus, I don't know, a little bit extra vector potential, some contribution. Now typically in mathematics or in physics, if you see a small delta, it probably means, you know, small compared to this one. I'm not making a statement like that. I'm just saying you have your original vector potential and you've added a little bit to it. This might be 15 times bigger than this one. I'm not making statements about magnitudes. I'm just saying vector potential plus extra. Okay? Now, let's see what happens to my magnetic field. Well, if I'm going to take the cross product of now the new vector potential, then according to my definition of my new vector potential, I'm going to get this. Going to get this, yes? But remember, what I really want is that my magnetic field that comes out here is going to be the same magnetic field as the one that came out here. So I've added something to my original vector potential, but in such a way that my magnetic field is still the same physics. Now, then we can immediately see what I should do to make that happen. Here I'm just writing out linearity of the cross product. Now this, if you recall, was my original vector potential, so this is just my B, yes? So if I want my magnetic field not to have changed because I've added a little bit of vector potential to it, what do you know about this thing?
0.
It must be 0. So what I'm concluding here now is I'm free to add whatever I want to my vector potential. I can add whatever delta A I want to it, as long as I make sure that that thing has a curl that is 0. If I do that, my magnetic field is not changed. Now, maybe you remember from one whiteboard ago that if you want the curl for something to be 0, then you can make a statement about that thing itself. Right? Remember the tangents from mechanics and such? I have something, I really want this to be 0. What does it tell me about my delta A?
It's a divergence of some function.
Exactly. So, if I choose my delta A to be the divergence, no, not the gradient.
The gradient.
Of some function, it's typically called lambda in this context. If I choose my delta A to be the gradient of whatever function, scalar function, lambda, then what I've seen here, well, then this part just vanishes, and I will get the exact same magnetic field as I would have without the contribution. So the conclusion here is, just a mathematical conclusion, nature, the magnetic fields that you actually measure, doesn't care whether you use this vector potential or whether you use this vector potential, as long as you make sure that this extra part is written as the gradient of a scalar function. Your magnetic fields will come out the same. Now, to be sure, it's the magnetic field that you want to come out the same because you measure magnetic fields. You do not measure vector potentials. You measure magnetic fields. Taking the classical mechanics connection one more time.
Conservative force or something like that?
Well, remember, if you have a potential energy that you can add whatever number to it that you want, it will not change your physics. Right? In classical mechanics, it's Newtonian mechanics. If you have your potential energy, only the amount of the change of the potential energy tells you something about what nature does, because it's a change of the magnetic of the potential energy that gives you your forces, the thing that you actually measure. So you can add numbers to your potential energy as much as you want. They will drop out anyway if you take the derivatives. So in classical mechanics, you already had some freedom. You could choose your potential energy in a certain way. Sure, it had to have this mathematical form, but you could add 10 or subtract minus 500 from it. Doesn't matter. You would still get the same physics. You see that the same thing happens here. You have a potential thingy, the vector potential, and apparently you can add whatever you want to it, as long as the thing that you add to it is itself the gradient of a scalar, and you will get the exact same physics. Big conclusion here: the scalar potential, the vector potential is not unique. You can add whatever you want to it as long as the thing that you add to it is itself the gradient of a scalar function. It could be any function. It may depend on time, space, temperature, whatever. As long as it is a gradient.
Time, though?
Sorry?
Can it depend on time?
Yes.
But what if we, because that says that the magnetic field doesn't change
Yes.
if we add anything, but then what if you add the electric field that is changing over time?
Yes, then you come into the non-static case, and then life changes a little.
So it cannot be dependent on time?
No, this still can. I mean, you can, doesn't matter. Because whatever this thing is, the curl of a gradient is always 0, even if the thing that you take the gradient of is dependent on time. But this is good news. That means that we have freedom in how we're going to choose our vector potential. That's what we're concluding here now. So if you have a vector potential that has the property that this thing is not 0, then maybe you can replace this vector potential by a new vector potential such that the new thing will make this thing vanish.
But yeah, but maybe there is something like inherently that makes that if we add a small variation of A that is a gradient.
Yes.
Maybe like there's an inherent property that makes that there is no way that it can be like 0 or like cancelled. I don't know if it.
Conclusion here is that you can add whatever to the scalar vector potential as long as the thing that you add to it is itself a gradient of a scalar.
Yeah, yes. But there is no guarantee that we can make such a thing that it will become.
That is a good question. For some reason, Vladimir, today you're asking all the right questions, because every question that you asked up till now in this lecture is exactly the point that I was going to make. So that's good. So conclusion now is, so really, I'm going to take your point and going to run with it. So the conclusion at this point only is that A and A primed, which by definition is the original A plus the gradient of any function, Both of them will give the exact same magnetic field. So the point here was that's good news because we have freedom in choosing our vector potential. So maybe we can choose a vector potential in such a way that this thing indeed vanishes. The answer is, that is your question now, right? Is it guaranteed that there is one particular way of choosing your A prime such that this indeed vanishes? Because that is not guaranteed per se. We've only found that you can add stuff to vector potential such that the magnetic field does not change. We have not yet proven that you can always choose it in such a way that this thing vanishes. So the next question is, okay, can we exploit this freedom to make this part vanish? So here's the question. What we want is that our newly defined vector potential, the one with the prime, has a vanishing divergence if we are given that the original A does not have a vanishing divergence. So this does not vanish, so therefore we're stuck with this. Question, can we make an A prime in such a way that the new thing does have a vanishing divergence? So can we make this one? The answer is yes, but we have to prove this. Boom, 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 boom. Suggestions. So you see the question, yes? We have a particular vector potential. It just so happens that this particular vector potential does not make this part vanish, but we have the freedom to add a little bit to it. The question is, can we add something to it that such that the new vector potential we end up with does have a vanishing divergence and this thing does drop out?
Can we rewrite the second term that shouldn't be equal to 0 or constant as a function and try to rewrite it in terms of A prime or something?
So you're saying that this
instead of
yes.
Instead of equating it to equal to not equal to 0, we can attribute it to a function or to something that is not like.
As in, there is some function that comes out.
Yeah, and try and see if we can build any function from A. And since we said that from A prime, and since we say that's.
I see that point.
And try to see if we can construct just by adding different gradient nearly every function. And
well, I think you're thinking in the right direction because certainly this is true. Certainly we can do this if we just find an expression for lambda that does the trick, right? If we have found a lambda that makes sure that this thing is 0, then we know that the thing exists. So let's just construct what this lambda must be.
What if A prime was the curl of something? Is the divergence of that would have to be 0?
Yes, yes.
So A plus gradient
Oh,
of
that is a
lambda
good point
is the
there.
curl of
Yeah,
something
sure.
else.
Yeah, so you're saying this. Well, if you want this to be 0, then you can certainly make that happen if this new A is itself the curl of something else.
Yeah.
Right? Because
If
the divergence
A
of the curl is
prime-
0.
If A prime equals nabla cross something
So,
else.
you're
No,
sure?
other way around. Just A prime equals the curl of a different field.
Yeah.
Yeah.
Yeah, you're right. Yes, you're right, yes. So you're saying, well, this is certainly true at the moment that I make my A prime, yes, be the curl itself of some new thing. And I'm running out of, so I'm going to, this is a silly function now, okay?
Yeah. That, although that doesn't help us find lambda specifically.
No.
but-
Oh, can we rewrite a cross product in terms of gradient? Or no. Because both are vectors, so basically we should be able at one point to write a gradient or a cross product in terms of gradients. No, isn't it possible to decompose a gradient, a cross product as a composition of gradients?
To write this
Because-
in itself as a gradient.
Because we know that this is going to be a vector, And I was thinking, like, maybe since also the gradient is a vector, there can be a way to write any cross product as a, I don't know, composition or sum or addition or whatever thing.
No, I understand what you mean. I understand what you mean. To write this out, and then maybe you get something that itself consists of scalar functions, and then hopefully read off what the lambda is or so. Might work, in fact. I don't know. I haven't tried it that way, but
wouldn't it be easier to just take the expression of A prime,
yes.
apply divergence on that, assume that like the divergence on A non-prime is zero, is non-zero, and then like see what lambda should be.
Yeah, I think that's the best way of doing it, right? I mean, we're looking for some lambda that makes this thing zero, but we know how to write A prime in terms of the original A and this unknown lambda.
And we're assuming that the divergence of normal A is non-zero, right?
Yes. So we want this to happen, but we have an expression for A prime. We have this thing, A prime, could be written in this way. We have proven mathematically that you can always do this without changing the magnetic field. By the way, I mentioned a second ago that we were going to grace this concept from theoretical physics called gauges. This is what we call a gauge. Just very loosely speaking, every time that you have a piece of mathematics in which you have mathematical freedom, you can add a little bit, you can subtract, you can take a tangent, you can take a logarithm, you can do something to the mathematics without changing the resulting laws of physics. That's called a gauge. More specifically, it's called a gauge freedom. Freedom in mathematics to change around functions in such a way that the physics that comes out is still the same. And here's a good example of this. Because we have the mathematical freedom to change stuff around in our mathematics, yet our magnetic field, our physics, is still the same thing. That's called gauge freedom.
Oh.
And that's good news because gauge freedoms typically mean that you can make your mathematics easier without sacrificing any physics.
Also, maybe something. Just.
Given the time, I'm going to write through this. This was Nelson's suggestion, yes? Nelson's suggestion was, well, we know how to write A prime in terms of the original A and this new thing that we still have to find, the lambda. Now, fortunately for divergences, linearity still applies, so you can just take the divergence of this thing and of that thing, and that will give you, well, the original vector potential, its divergence, well, plus the Laplacian of this yet unknown lambda. And it, by definition, you want to be zero. So that means we have an expression that our unknown function lambda has to obey in order for this thing to be true. Right? If we can find a lambda that obeys this equation, then we have made sure that our new vector potential has a divergence of zero. Has anyone ever seen an equation like this? Maybe in multivariable calculus. It has a name. In fact, forget about this part that it happens to be this complicated itself, divergence and such. This one. You have the Laplacian of a scalar function and itself equals some other function. Anyone ever seen an equation like this? Maybe if I call it by its proper name. It's the Poisson equation.
Oh, yeah.
So you see that this expression is just this expression, yes? I mean, what I call lambda is what is called f here. The source, it's called the source, S, is in this case is the divergence of another thing. This thing is called the Poisson equation. And one of the exercises of the tutorial is to solve the Poisson equation regardless of what S is. In fact, I'm going to give you the solution. It's up to you to prove that it is correct.
I had an idea maybe, but it's more of a linear algebra idea. So we can say that we have a vector from A prime cross product nabla C, S, sorry. And then we know that that is a three-dimension vector. So we can choose three function that will each create a set of coordinary, and we'll be able to express any vectors in terms of those coordinary, you know?
Yeah, I understand, but how does that help? What you're now saying is...
Because if I can say that I can write alpha prime as a sum of at least three at the sum of at least three gradients, as a linear combination of the sum of three, as a combination, yeah. We can write alpha at a prime as a combination of linear combination of three gradients. Not gradients, three functions.
Sure, yes.
And then, because we know that that is, if we have a gradient that is equal to 0, then we find that we can always have like a 0 field, no?
Yeah, but I mean, we will have to sit down and work this out. I mean, I have no immediate way of telling whether this will work or not. I understand the methodology, it's just to know what's going to come out.
Mm-hmm. But I thought it was just like, if we can build any vector, isn't like directly like already like, if I can say that every vector of a prime can be constructed just through gradient function, a combination of gradient function, would it be enough?
No, because what you're then doing is going back to what you started out with. The beautiful thing was here that we have reduced this extra part to only, right? The original thing was we added, it's removed now, but the original thing was that we added another part to the vector potential. Wait, just a second.
Okay.
We added another part.
Mm-hmm.
And then we noticed, so we had to add three different things, right? It was a delta A in three directions.
Mm-hmm.
And then what we saw here was, wait a minute, but you can write the whole thing as only one function. Mm-hmm. And now you're suggesting, well, let's take that one function and split it up again into three functions. So that doesn't...
The only thing that I'm saying is like, since we said that in order for A prime to be the same, to be able to be cancelled, anyway, I'll try to...
Yeah, sorry, Vladimir. I mean, you have a suggestion, which is perfectly fine. It's just, I have no way of checking whether that's correct without sitting down and doing the exercise. And I don't think that this is the time.
Sorry.
No, that's fine. It's a good suggestion. It's just I have no answer for you without doing the exercise. So, but this works, yes? I mean, we have now seen what this lambda should be in order to make the divergence drop out. But that means we do have to find a solution to this differential equation. And again, this is called the Poisson equation. It's going to be very important for the whole rest of our course. We're going to apply this many times over. So one of the exercises is going to be check that the solution that I'm now going to give you is indeed the solution to this equation. So I'm going to give it to you now. It's 1 over 4 pi, big friend 4 pi, with a minus sign. And you're going to take the original source S, there you go. Looks familiar, doesn't it? So what did I write here? I said, well, take the original source. You know, maybe for notation to connect it better to what we've seen before, let's write everything in terms of R. Okay. So you remember what big R was, yes? What's the difference between this R primed and the R where you're actually interested? This looks very familiar, probably, because we had already proven at some point that, in fact, it's still on the board. It very much looks like this thing, except there's no square. Aside from that, including the 4 pi and a minus sign, all of a sudden, it's the same thing, including the primed and this big R coordinate. Very much the same thing, but there's no square. That's an exercise for you to prove that if you take this thing, put it in here, you will indeed get back S. So this is the general solution to this Poisson equation. So I'm not postulating this for you. See tutorials to see the actual, that is actually true. Now, let's apply it here. We have a Poisson equation. This is then what we would call S. This whole thing is what we call S. You tell me, what is lambda as a function of location?
No, it would be the thing on your right, right?
Yes, but
-1
okay.
over 4 pi.
Okay. Yes. Continue. Yes.
Integral of the thing that you pointed out it was S. That means the divergence of A.
Okay. So this
So
minus
the minus
negative
goes
divergence
plus
is
divided by R. dv.
integrated over all the space. Yes. Now, no one is ever going to ask you to do this integration. Then why the hell am I writing it down? Because the fact that the thing exists means that this lambda exists that make this divergence be 0.
How do you know it exists?
Sorry?
How
Because
do
you
you know
have
it
an
exists?
expression for it.
We have an equation, don't we?
Yeah.
We have an expression for it.
Does that exist for all values?
If I were in a situation where I start with an unprimed vector field and I find, wait a minute, its divergence for my vector field is not 0, then I've seen here, but wait a minute, I can add something to it and I get a new vector field, and that new thing's divergence will be 0. Yes?
Okay.
But then the question is, okay, but can I choose a lambda such that that works? And the answer is apparently is yes.
What are the limits of the integration?
Oh, that's a good thing. All space. All of the universe.
But what if it just doesn't converge or something?
That is a good point. We have an expression, and I said, well, therefore the lambda exists. Well, if it doesn't converge, then we're in a crappy situation. I agree with it. I agree. So I'm taking a little bit of liberty. Now, in practice, it converges. And you know how physicists are, they say we have an expression, and there's probably some mathematical subtlety in some cases. Let's not worry too much about it. No, in practice you will find that this works. Now, nobody's going to ask you to calculate this thing. The only thing that the whole exercise here is just to show you that this lambda that makes, okay, this thing go to 0 can indeed be found. So again, one more time. Suppose that I do this exercise. I go through my electrodynamics and I find that I have a vector field here, which unfortunately doesn't has a non-vanishing divergence. Okay. Then I say, well, I'm just going to add something to my vector field, such that my new vector field does have a vanishing divergence. So all of a sudden, this is gone. But then, how do I have to choose this thing that I add, this lambda? Apparently, I just have to take this vector potential that did not have a vanishing divergence. So this is not 0. Divided by r, integrated, divided by 4 pi, and then I have my lambda. And then I have the lambda that makes sure that my new one is indeed, my new vector field is indeed, has indeed a vanishing divergence. So that's a long sentence to parse, but you need to see a series of steps here. This does not vanish. I have a freedom to add something to it. What do I have to add? If I add this, or the gradient of this, then my new vector potential will have a vanishing divergence. So, long story short, this gauge freedom that we have, the freedom to change a little bit about the mathematics in such a way that I don't change my physics, in this case the magnetic field, allows me to always choose a new vector potential such that this is 0. And then I'm in the situation that I promised before, that you have 2 times the same equation. That's abstract, isn't it?
Mm-hmm.
But that's the way that it is. I mean, I've said, unfortunately, it becomes more abstract, but it becomes much more easy to work with. So, again, we can always choose it such that this divergence part of that equation vanishes. How do I have to choose it in that way? I'm not going to ask you to calculate the thing, it's just a proof that the thing exists. Now we have this, and we're all done. Gets a little better still.
One small question about
yes.
that. You say that we can just replace the a for any a prime that we want. Will that at least make sure that that one term vanishes?
Yes.
We do still leave the original a in the equation there, then, or do we not?
Yes.
We do leave it there.
Yes.
Okay.
But I mean, I'm just dropping the primes. I'm just dropping the prime on that. I mean,
It's the same thing.
it's now the same thing anyway. So, okay. Now, this particular choice of having chosen my lambda, that is what we call a gauge. We have a gauge freedom. We can do something to the vector potential such that magnetic field doesn't change. This particular choice has a name. The choice that makes this divergence go away is called the Coulomb gauge. This is the name of the thing. So this is true by having chosen the Coulomb gauge. What is the Coulomb gauge? It's you choosing your lambda in this way. That's just what the trick is called. All right. Good. We've done lots of work, but we have now a very beautiful point because we have now two very easy equations that we can now solve and get to the full electromagnetic field. But we still have to solve this equation a piece, yes? And I'm waiting for somebody to see if the parts come together. Just stand back for a while. Maybe you want to connect the left-hand sideboard to the right-hand sideboard, maybe.
If you can somehow like show that those two together form a 4 vector, then you can like solve the whole thing in one go, right?
No, that is very true, because I did promise at the beginning of the lecture series that when we've gone back down to 4, which we have done now, relativity will bring it back down to 2. So we will do that, but not today.
Okay.
But you're right. We have 4 equations now, and they can be reduced even further to only 2 if you add special relativity, but we're not there yet. My question is, okay, you have this equation, forget about the divergence, go now. Wouldn't it be good if we had the solution to these equations? Just again, going to stand back, left-hand boards, right-hand boards.
Get something with the Poisson equation.
I feel like it, yeah. Yeah.
Compare this one to this one.
Yeah.
Mm-hmm.
It's a Poisson equation.
Mm-hmm.
And wait. Compare these 3 to 3 times this. We have 4 Poisson equations. And here's the good news. Here's the solution to all of them. So I left a little space blank here. It says solve for this and this. We don't have to. The solution is right there. So let's put in the details right here, right now. So you tell me, what is the scalar potential given the solution of the Poisson equation? Yes, I'm waiting for somebody to dictate this to me.
Minus 1/4 pi.
Okay. Minus.
Oh no, not minus.
Because this minus is cancelled, yes.
Integral. Well, yeah, I'll leave the email. Integral of the charge density over R.
There you go. There's a solution to the Poisson equation. No, because without this, you would be right. So this is what I promised. The full solution for all cases, all electrodynamics. Well, statics. I haven't put in the dynamical part. Now how about this one?
We have 3 components.
Yes, but we can all write them down into one equation.
Yes. Depending on
1/4 pi. Integral of mu naught current. Mu naught over 4 pi. Integral of current.
Current, yeah, sure. As a function of r prime.
Yeah, over R.
There you go.
R prime stand for
R prime is the coordinate that integrates over all space.
okay.
Yes.
So those are the same as the E and B expressions, except with one less factor of R.
Yes.
Because they are the gradients of the.
Yes.
That makes sense.
So you can now forget about this part. What we now have is a beautiful series of steps. Somebody gives you a charge density. Somebody gives you a current. And instead of solving this complicated set of 8 equations, you know what, just solve these 2. You know what? You don't even have to solve it. It's already done for you. Here they are. Here's the solutions. You still have to write out what the integral actually says in your particular case, but here's the full solution. You will get your scalar potential, you get your vector potential, put them back into these equations, and you have the full solution. This is for all cases. It's always true. Well, given that the Coulomb case holds. Yes. By the way, if the Coulomb case does not hold, what should we do?
Cry.
Cry. That is one option, and after you're done crying, what would you then do?
Just add the other term with the
Yeah, the term that apparently we cannot move away. It just means that you will still have this extra term here, and it just means that this part of the solution will not hold anymore. You would have to go back to the drawing board and find its solution. So, I said at the beginning we have to do a lot of mathematical work, but at the end I think it's worth it. 8 equations reduced to 4, and I've given you the full solution to all 4. There's that.
Beautiful. But then in practice, how do you?
I give you a charge density, I give you current. You go through these series of steps. At the end, you have the full solution.
So no, the usual thing is we get charge or current, and then we have to find out the scalar E.
Usually, in practice, what you usually get is that somebody hands you how much charge there is in a particular piece of volume, and or how many current there is. So somebody hands you this function and that function.
Okay.
Right? And you can put them in here and then solve these 8 equations, or you put them in here, solve these 4 equations, for which the solution is already given to you. So it's obviously much easier. Now, in the 5 minutes that we have left, we certainly cannot go to the case where, remember, we had put this to 0. All of this is for statics, and time derivatives are 0. Now, what I think that I will do is the derivation for full dynamics, where this is not 0 and this part is not 0, is very similar. You will, in fact, get very similar results. You get another series of steps, and it's almost the same, just a small variation. Now, certainly we cannot do this in the 5 minutes that we have left, so I think I will split this up and make those as extra exercises. With what you see now, you should be able to solve that. But maybe we can sort of already hand-wavingly go through this. First of all, remember why we're allowed to write your B field as this? Do you remember why that was? Going all the way back to the beginning of this lecture.
Because the divergence of a curl is 0.
Yes, because the divergence of a curl is 0. That was a mathematical fact. That allowed this to write as such, right? Now, here is something, the divergence of something, that is 0. At the moment that I put back my non-static part, I put the dynamics back in, will this equation change? No. Right? I mean, if I put back my DDTs, well, this changes and this changes, this will stay the same. But that means all the argumentation that led us to conclude that you can write B as the curl of an A is still true. So that part, all the magnetic part, has not changed whatsoever. In fact, this part with the gauges has also not changed. So putting back the statics will not change anything about the magnetics. That part is still true. But remember that we had the electric field, we could write as minus the gradient. Under what condition was that true?
Curl of a gradient is 0.
Yes, that the curl of the electric field was 0, but that, if you add back the dynamics, is not true anymore.
Yeah.
So that means that this thing is not true anymore. You have to do something extra. So the electric part needs some modification. Now, what I promise you, and I will just turn that into stepwise exercises. What I promise you is that this stays the same, this becomes a little bit different, but you can follow the same series of steps and end up with the same equations. So this will still be the same, this will still be the same. It's just that given, so one step back, sorry. If you go through the series of steps, you will find that this has stayed the same, this has not stayed the same, there's a small variation there. But you will find that this is still true. So you can still find your scalar field and your vector field in the same way as before. It's just how then you turn this vector field and the scalar field into the actual magnetic field in the electric field. That part has changed. But otherwise, still the same mathematics, still the same ease. But again, I will turn this into an exercise. So, any questions?
What about the one big equation?
What about the one big equation? What about it?
You said there was going to be one equation for whole of electrodynamics.
Yes. There you go. But we're going to get there in week 6, okay? But this is the final one. The big F there is the Maxwell stress tensor, and it's one big tensor. What the hell is a tensor? Again, week 6. It's one big object that contains all the information, and you take its derivative, and well, there's a notational issue there. It's a contraction. It's not just one derivative. It's a sum of multiple derivatives, and it's equal to the total amount of current.
So it's still 4 equations.
It's still 4 equations, but written as one.
That's cheating.
A little, yeah, I agree. Okay, so thank you. We'll upload either by tonight or in the course of tomorrow, including the exercises and such. So thank you very much. Hope you're not too saturated. Let this sink in for a while. Enjoy the beauty of the thing. Look. And I will see you in 2 days.